We learned how to evaluate a double integral over a rectangular region by using the result of Fubini's theorem. The integral can be evaluated as a series of iterated integrals, which boils the integral down to single variable integrals. Now remember that the integral will exist if the function f is continuous over that rectangle or piecewise continuous over that rectangle. How can we calculate a double integral over a region that isn't rectangular? Now we're going to consider a special case that covers essentially all regions that we would encounter in practical situations. The basic idea is that we are going to enclose this region within some other rectangle, and we're going to then define a new function that contains our old function but is extended over this new rectangular region. This region D is bounded, and bounded in this case means it can be contained within a rectangle, and it has a finite number of continuous curves forming its boundary. So that covers things like straight line boundaries or some sort of curved boundaries. So we are now going to create a new function, capital F of x and y. It's defined as a piecewise function equal to the original function over this region D. And then it will be 0 if it's in R, but not in D. So this is known as the extension of our function f to this rectangle R. We are going to assume that the function f is continuous over this region D, and that means there's going to be a jump in value. So if we took a look at a different sort of picture here, you could imagine that right over that region D, we can define this other rectangle. The value of the function is going to be non-zero here. It will have a 0 value everywhere else. So clearly there's going to be some sort of discontinuity in the values of this extended function f. F will be piecewise continuous on this rectangle R. But we already know from the previous video that this implies that f will be integrable on R. That means this double integral of the function will exist. And then we define the integral of the function little f over the region D, the one that we're truly interested in, as the integral of the extended function over this rectangle R. So that is going to be the way in which we extend what we learned about before to try to deal with these cases where the boundaries are not simply rectangles. Another important idea here is that all of the properties from integration on rectangles apply. And in particular, the one that we are interested in most is saying if we have some sort of rectangular region that's a finite union of disjoint regions, so let's say R1, R2, R3, etc. So if R is a union of all of these individual regions, then what we can say is that the integration of some function over that union is simply then the sum of all of the individual integrations over those individual rectangles. And that's going to be important for us when we try to define how to evaluate these integrals. This D is going to be what's called an elementary region, bounded by continuous functions and finitely many of these continuous functions. So we can talk about a type 1 elementary region. Here, the value of x is bounded by 2 values, but y is going to be bounded by some continuous functions of x. We're going to have some straight line boundaries for the x values, but down here, we'll have a continuous curve, g1 of x, and then up there, we'll have some other continuous curve, g2 of x. So again, g1 and g2 are continuous curves on this interval AB. We are going to think of this in the way that you do in Calc 2, where you have some coordinates here that look like this, and some coordinates down here that look like that. A type 2 elementary region works very similar, except the y value is bounded by some constants, so your y integration ranges from c to d, and then your x is bounded by some continuous functions of y. And so again, in terms of a picture, you've got your integration range here, c to d, and these are constants, and then there are some continuous functions here, h1 of y and h2 of y. And again, h1 and h2 are continuous on this interval c to d. So as before, it's going to be helpful for us to think of a slice, an integration slice here. This point would have y, h1 and y. This point would have coordinates y, h2 of y. Now there's a third type here. This is known as a type 3. A type 3 region is both type 1 and type 2. So you might say, how could a region be both type 1 and type 2? Now a simple example here would be the unit disk in R2. The set of points x, y, such that x squared plus y squared is less than or equal to 1. Now the unit disk looks like this. It's a circle of radius 1. This unit disk is bounded. We could keep it within some sort of rectangle. If you wanted to think of it as a type 1 region, that means we're going to have values of x that are constant, but we are bounding it in the y direction by functions. We would go from -1 to +1, and then the upper curve there would be the square root of 1 minus x squared, and the bottom curve here would be -1 minus x squared, like that. So the region D, the set of all points x, y, such that x is between -1 and +1, and y is between these two values here. If we wanted to view it as a type 2 region, we're going to take a similar approach. We are going to think of this unit circle as being bounded in the y direction, and then it has two curves. This curve here would be -1 minus y squared, and this curve here would be +1 minus y squared. So the region D in this case would be the set of points x and y, such that y lives between -1 and 1, and x lives between these two continuous functions of y. So how do we actually compute this integral over some general elementary region? We're going to assume that f is continuous on this region D. So there's our region D. This D is going to be contained within some box, alpha to beta, gamma to delta. This forms our region R because we have to define the extended function. We're going to assume that we can describe this as a type 1 region. This region D is trapped here between some values A and B. Alpha will be less than or equal to this A will be strictly less than B, this will be less than or equal to this beta. Now up top we're going to assume a G2 of x there and a G1 of x down there. So that means that these values will also serve to bound those bottom functions. Now, just as always, we're going to define this extension function. The extension function is equal to the original function on D. It's going to be equal to 0 on all the regions in the rectangle if we take away that D. So when we talk about computing an integral over this region, remember that this is going to be piecewise continuous on R. So that means that this integral will exist. Furthermore, all of the properties that we want to use can exist. Now, the important thing here is we are going to subdivide this. We're going to take this region and break it up into 3 non-overlapping rectangles. R1 will be this area to the left, R2 will be the rectangle containing the blob D, and R3 will be this rectangle over here to the right. We could calculate this as a sum of 3 individual rectangles. I'm being a little bit sloppy with my notation here. On rectangle 1, the function is 0. On rectangle 2, I'm still going to evaluate what the function is, so I'll just leave it as capital F for now. And on rectangle 3, I'll have a 0. Now, if we look again here at rectangle 2, it's bounded from little a to little b. So what happens is that if I'm interested in calculating things on rectangle 2, this is going to be by Fubini's theorem, iterated integral, from a to b, and then I'll have an integral here from gamma to delta of this function because I'm just bounding it by that rectangular box. Now within that rectangular box, I'll have from gamma to g1 of x, the function will be 0. From g1 of x to g2 of x, the function will be little f. And then in the third region from g2 of x to delta, the function will be 0. What happens here at the end of the day is that the extension function defined over the full rectangle can simply be computed as this iterated integral. Involves the original function evaluated from y and then evaluated from x. Now, similarly, if we had a type 2 region, evaluation of this function over that region is simply just going to be an integral from c to d, h1 of y, h2 of y, function integrated over x, then integrated over y. Now, if it's type 3, what you do is choose to divide it into either a type 1 or a type 2 region, and then you add them all up.